Hi guys, welcome back to Data Every Day. Today we're looking at a data set of electric motors, and we're going to try to predict the temperature of a given motor. Now, this data set is very clean and has already been scaled and processed. There are no missing values. So let's just hop in. I'm going to do some EDA today to make up for the lack of pre-processing work. Alright, so we're going to use just a linear regression model today, nothing fancy. I'm going to use NumPy and pandas to work with the data, and then matplotlib.pyplot and seaborn to visualize some of the columns. And we're going to use the standard scalar and train test split function from sklearn, also for pre-processing. I know that the data is already scaled, but I'm just going to scale it again just to be safe. And then we'll use just a linear regression model to make our predictions. So I'm going to go ahead and import that and store the data in data. So pandas.readcsv, and we can get the file path up here, copy it, paste it in, and take a look. And this dataset has nearly 1,000,000 rows, 9.98 100,000. And so it looks like we'll only use, well actually let's get a little information just to see if we have any null values, and no, we do not. We also have everything in numerical form, so we're just ready to get in. There's very little pre-processing going on here. Let's make a function though, pre-process inputs, that's going to take in a data frame, and it's going to return x and y, where x is what we're using to predict y. So y here is going to be just the PM column. PM is the temperature measurement. That's what we're going to be predicting. So I'm going to make a copy of that column, and then x is going to be everything except PM. So I'm dropping it from axis 1, and I'll make a copy of that as well. Then we're going to, well, we can just do this right away, but first I'm going to make a copy of the df at the top, and we'll store the result in x and y down here. So pre-process inputs, and we're going to pass in data. Now we can take a look. X and Y, and so this is the value we're trying to predict, and X is everything we're using to predict it. The only thing I see is we're not going to use this profile ID. Actually, I guess we could use it as a nominal feature, but for the purposes of the video, I'm just going to drop it. So df equals df.drop profile ID from axis 1. Now we have x without profile ID, and additionally I'm just going to scale it as well. So let me comment this a little. I'll say dropping profile ID column, and let's split df into x and y, and drop. Alright, and now last thing I want to do is scale x afterwards. So I'm going to create a new scalar, which will be a standard scalar from sklearn, and we can scale it with scalar.fitTransform x, and store that back in x. And since this returns a NumPy array, I'm just going to turn it back into a data frame when we're done. And I'll keep the column names the same as they were before. Alright, so now it doesn't look very different because it was already scaled, but I didn't scale the target because maybe maybe it was important the way that it was scaled beforehand. So now I guess it's ready to get fed into the model. It's all we needed to do for pre-processing. Why don't we start some EDA? So we'll start with a univariate analysis. So looking at each column one by one. And well, let's get a little information. Well, actually, you know what I want to do is I want to put together the x and y just temporarily so that all our EDA will be performed on a separate copy of the data frame. So I'll call it EDA-df equals pandas.concat x, y, and I'm concatenating them on axis 1, and I'll make a copy. So this is the data frame we'll use to explore. So we'll start by getting a little information. EDA-df.info. Well, we already did that. Let's just do describe. This will give us some statistics about each column. We can get the count, mean, standard deviation, minimum, the percentiles as well, or quartiles. and then the max. So I'm not going to go too in depth about all of this, but if you want to take a look, go ahead. I'm going to get some visualizations going. So what I'm going to do is I'm going to plot the distributions first using the Seaborn dist plot. So we'll create a new figure with matplotlib, fig size 16 by 12, and for I in range, length of EDA_df.columns. So essentially what we're saying is for each column indexed by I, we're going to create a new subplot in a 3 by 4 grid indexed by I plus 1. And we're going to create a new Seaborn dist plot of EDA_df sub, well, if I want to get the column name, I'm going to do EDA_df.column sub I. Alright, so we'll index the column list at I, and then index EDA_df at the column name. Alright, and when we're done, we'll just show the plot. And this shouldn't take too long, but it may take a little time because there are a million data points. Okay, so here we go. So this is what we're trying to predict. Note that it does take a normal distribution, and most of these do as well take some sort of normal distribution, except maybe, I don't know, some of these have this big spike around the mean, and this one actually a big spike below the mean, so maybe not so normal, but these bottom ones definitely normal. It's interesting. This one has a big spike past the mean as well, so it's good to look at. Then I also like to get some box plots so we can visualize if we have any like extreme outliers. So what I'm going to do is just grab that, paste again, and then instead change this to box plot. And that should just take about the same amount of time, or even less. So we can see really not too many outliers. This is the only column where it looks like we have some maybe extreme outliers here. If you're not sure what a box plot is, basically this is the median in this line in the middle of the box, and we have on the side, this is the first quartile, the third quartile, and then these lines on each side are the 1.5 times the first and third quartiles respectively, subtracted away from the median. So this is a good indication of when outliers start showing up. So if we have these dots that show up outside of the line here, we know that these can be considered outliers. And if you see they're all grouped together like this or like this, they aren't really outliers. It's more of just like a taper. But if you see we have little bits all the way far away, they could be troublesome. And these aren't so bad, but you know, the farther away they are, the more they can negatively affect the performance of a model. I'm not going to go through filtering them today, but we could actually just remove those if we wanted. Okay, and then the last thing I'm going to do for the multivariate analysis is actually, no, sorry, I'm done with the univariate. I'm just going to move on to the multivariate now. So this is looking at the relationships between columns. So let's start by getting a pair plot for the whole data frame. I'll create a new figure. We can make it 16 by 16. Whoops. And I'm just going to do sns.pairplot. Now, if I just run the pair plot in the whole data frame, it will take a really long time to load. So I'm just going to sample 1,000 points from the data frame and use that instead. So we'll show that, and this may just take a moment, so I'll pause the video and return when it finishes. Alright, it finished, and you can see we have a very interesting pair plot here. Each column and row represents a different variable, and then the intersection between two is the correlation. Well, it's actually just one plotted against the other, but we can see any correlation in the data this way. And you'll notice we have some really intense correlations. This looks like almost a perfectly linear correlation. These also are very high, very strong positive correlations. And we have some very interesting shapes like these parabola types. It looks like, for example, in this one, before the mean, we have a positive correlation where as one variable goes up, the other does as well. But then after the mean, it reverses. As one goes up, the other goes down. And you can see that's sort of repeated across here. This one is interesting as well. It's saying as one goes up, the other converges to a point. And on the other side, not for both cases. Um, it's so interesting. Oh, it's actually just flipped. Oh, no, no, no. Okay. Oh, so it's hmm. This is very interesting. Right, as one goes up, the other goes up, then down. But if we look across it this way, as this one goes up, or it's the same thing as this going across, the points converge. So that's very interesting, and you can see we have a similar thing here, and where is it? It should be flipped over to here, here and here, right? Uh, hmm, that's very interesting. The shapes that these are making. And then over here we have a lot of very low correlation in the data. So I'd like to actually plot the correlations as a heat map so we can sort of match it up with this pair plot. I'm going to create a correlation matrix called core from edadf.core. And then I'm going to create a new figure, how about with fig size of 12 by 10. And we could seaborne heat map here, pass in core, and then turn on annotations. I'm also going to set the minimum value of correlation coefficient to a -1, and give it a color map of Mako so it looks nice. And we'll show. Alright, so you can see we have some really high correlations here, and what's most shocking to me here is that we actually have a correlation of 1 here. So it means perfectly correlated. So yeah, look at this. This guy has the correlation of 1. This and this correlates to this and this. And then over here, we have some very high ones. So you may say, okay, we can drop that because it's perfectly correlated. We don't need 2 duplicate columns. And we could. I don't think it's going to affect the performance so much because if you look, they're actually not completely duplicate, right? They're slightly different, but certainly as one goes up, the other does. That's very, very evident from this. And if we were working with a really big data set with a lot of different features, we definitely want to remove these. But because we have so little information, because we only have 11 features here, yeah, we only have 11 features. It's not going to affect the performance so much, but we definitely could drop it if we wanted to. We would drop one of them and keep the other. And we're going to, I guess that will conclude the EDA. We'll start training now. Okay, so we have our X, right, and our Y, and we're going to try to split them into a train test set first. So X train, X test, Y train, Y test equals train test split X, Y, and we'll give it a train size of 70% and include a random state so that because this function shuffles the data as well, the random state ensures the shuffle will always be the same and the split will always be the same. So this will give us 4 new sets of data, and then we can create our model, which will be a linear regression model, and fit the model to the train set. So X train, Y train. And once it's fit, we can print out the results, and this will be the score of the model will be given in R squared score, which is essentially a measure of how dispersed the data is from our fit. So we're going to print model R squared score, and we will format it with 4 decimal places, and we'll plug in model.score, and this we're scoring on the test set, X test, Y test. And we end up with an R squared score of about 0.77, which is very good. I mean, fairly good at least. This is definitely good. I'm sure if we tried out some other models and tried to optimize them, we could get something better, but I'm not really going in depth today, just doing a quick training and EDA. So that will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.